Hey, Thomas.
Hey, Luca, what's up?
Yeah, different environment. I'm in California. Uh, I don't know
Yeah,
what time it is right now. But I happen, you usually come here, don't sleep. So I said, yeah, for sure. 6:37 is gonna be great. And turns out my biological clock adapted immediately to the new time, and so I just woke up. So anyway,
yeah. So, thunder
anyway.
session in the morning.
Yeah, yeah, I love thunder in the morning. So let's do this. Let me recall now that I just woke up. Where did we left off? Oh yeah, so we're doing the activation checkpointing. So let me share my screen.
Right. You had the
So
right sketch, right?
exactly here, this was the sketch. Um, so let's get back to it. Maybe this one was a nicer version. You have the forward here, and you have your model. You compute the forward, and in computing the forward, you compute intermediates. Intermediates are like, for example, all the activations after
Right.
an individual layers. And then I'm drawing blocks here because a lot of the models that we're interested in are blocky. You have attention, MLP, attention, MLP, attention, MLP with a bunch of other operations in between. And so you have a sequence of these blocks. And then when you need to compute, you go on to compute the loss, and then you call backward on the loss. And when you call backward on the loss, you need to basically enqueue a few operations after the backward, which is the backward pass, that will need these intermediates in order to compute the partial derivatives of the loss with respect to the parameters. And these intermediates are not necessarily cheap to store from here to there. And so this is why we drew a lot of arrows here, because you will use this intermediate right away, but then you will use this intermediate at the very end. And so this means that you need to uh, store a lot of stuff, and storing a lot of stuff on the GPU is expensive. Storing
Yeah,
it on,
basically, your
yep.
memory graph has a mountain, and the question is
Oh
your
yeah,
GPU like fit enough to survive climbing that mountain, right?
exactly. It goes this way, right? Because then, well, sorry, the loss is here. So the mountain ends here. Apologies. Let's do this again. So this is the thing, and you have the mountain until the loss, and then you go down because you can start deallocating stuff. Now, yeah, uh,
Yeah,
will your
but you end
GPU
up with
survive?
gradient
Not really.
tools.
Yeah. Oh, yeah, yeah, exactly, exactly. This is the memory for the activations. And then you need to store, of course, whatever you're computing here. And so, because then you need to use them for the optimizer. And so, yeah, the memory, yeah, there's never enough memory. Interestingly, there are cars now that have a lot of unified CPU memory on the chip. And so offloading this to that main memory would be interesting in the future. But we're not there right now. So, well, not with most GPUs. So once something is on the GPU, it needs to stay on the GPU if you need it right away. Otherwise, you will incur in latency offloading to CPU.
Yeah. Obviously,
Okay.
if you want to hear more about this offloading to CPU, you find my address in the links and you can send me one that supports it.
Yeah, yeah, maybe, I heard that there might be something coming in our Lightning Studio at some point in the next few months. And so, yeah,
Right.
that would be interesting. All the Grace, Hopper Grace, Blackwell architectures. Yeah, being able to
Yeah.
play with those. Yeah. So anyway, where does this leave us? Well, it leaves us with not storing all this stuff. And since what we're computing is kind of blocky, then what we can do is what we were drawing here, um, we had this quote idea where we only store one intermediate every once in a while. Then you can decide the granularity. And then when you need these intermediates here, you just recompute the forward and build the intermediates for a very short time, and then use them in whatever block you need them for the backward, and then deallocate them. And this,
Right.
you're basically trading computation for some memory, or memory with computation.
Right.
Excellent. So
It's like I never can remember things, and so I have to go back home and fetch them after I arrived at the store. There's a new restaurant in my neighborhood, and
yeah,
you bring your own, or they have like it's a to-go thing, but you can eat it there, but they don't have cutlery. So I always bring my
Oh,
own
really?
fork and spoon. And if I forget, I need to walk back and fetch it.
Interesting. I didn't know this was the
But
new
yeah,
wave. It will come in Italy too then. All right. So I
so
think we can start.
let's look at how we do this in Thunder, and
Yep.
maybe because it's like for a large model we get all the large things, but let's start with a small one.
Yep.
And so
But you need to
we
share the
import.
screen, my friend. You need to share the screen.
I can hear you, Luca.
Oh, you need to share the screen.
I need to share the screen.
Yeah.
It would be so much easier if I could hear the co-host, but yeah. So let's share the window with the live demo. And
yeah, sorry, I'm in some kind of network situation that is not very stable.
Okay, so here it is. We import Thunder and we import Torch, and let's just have a small model as a demo. So we have Thunder, Torch, and then sequential. And this has, let's say, Torch, and then linear, and 2020, 1024, 1024, and maybe 248. And then Torch, and then linear 2048, 1024. But in between we need an activation, Torch, and I'll just use Relo for now. Good old Relu. And so here we have the thing. And of course we can Thunder JIT it. So Thunder JIT of the model. And then we run it, right? We need some inputs. Torch random, and let's say 1024. Okay, so with this,
you hear me now?
we can run our model. What did I do now? We can run our model.
Maybe not.
And we get the function, and we can look at the traces. So last trace of JM, the last one is this one, and we know this. Here there's a linear, and then there's the relu, it's decomposed, and then there's the other linear again. And so if we look here, it saves like everything, right? It saves the T3. It does not save the output of the first linear because the relu will just use the T12, and then it saves the T6, which is like the output of the relu, and it saves the T12, which is this comparison matrix, which is different to what Torch does. It just checks again. And then here we have the weight input and the other input. And of course, we don't need to save the output because we already keep that anyway. And so we have that, and then the backward uses them, right? Thunder last backward traces, and this has twice as many mud molds, but so the main thing here is that you have the saved for backward, and the saved for backward has the weights that we saved, obviously. And so now, how does that change when we do this? And so ideally, and this is one of these the sausage is made moments. Ideally, we would have a transformation that we would do here, but it's actually not a transformation, but it's slightly different and is a flag. And you have to remember what the flag is. Enable saved for backward recomputation.
Hey, Thomas, do you hear me?
That,
oh no.
We have we can rerun the model, and it does the exact same thing. But if we look at the last traces, we see that here it now doesn't have any intermediates to save. In particular, here the T6 is gone, and the T13 is gone. And if we look at the backward traces, we see that these are actually recompute. So we have here that we recompute the exact thing, the T13 and then the T6. And so that's all the magic, but you need a thing that actually identifies, like, what do we not want to recompute, what do we not want to save. And here you see already one of these themes is that all the ultimate inputs you can just keep because there's no way to recompute them. And for the weights, they are around anyways, at least until you update them. Yeah, so Luca.
Do you hear me?
Now you hear me? I have the trouble that I can't actually hear you.
Okay. Can you
now I can hear you again.
Okay, great. Yeah, because as I said, like, my network is not really super stable, so I had to switch in between. So that was great. So why is that a flag and not a transform? Because it is a transform, actually. Yeah.
So what we have is, if we look at let's do it in the same notebook. If we look at the transforms that we have, and this is in Thunder core transform common transform. If we look at the class, we see that there's various hook points. So there's one transform traces pre-prolog, and we've used that a lot in the previous sessions, which is kind of the workhorse. After we acquired the model and before we actually run anything, before we run the prolog, this gives us a chance to modify the prolog trace, the computation trace, and the epilogue trace. And you can do all sorts of things, from taking gradients to quantization to distributed. They can all work with that. We also have a transform module, which actually transforms the module before tracing, which can be convenient in order to, like, modify the tensor, the weights when you split them for FSDP or something like that. Or if you want to quantize, you need, like, replace the weights with quantization and dequantization information and things like that. And then there's also something to transform state dicts in order to enable, like, loading the original or the transformed state dict as you want, and go back and
this forth. Is one of the funny things in writing transforms, right? Like you say, oh, okay, great. Now I have quantization. Now I have distributed. The next question is, how the hell do I get the weights in if I save them from a checkpoint? Or how do I save the checkpoint?
Right.
That's the moment where you realize that you have twice as much work to do in front of you.
Yeah, but interestingly, if you have this along your transform chain, you have like go forward and go back. And so, for example, for distributed, going forward is like splitting the weight for FSTP. You split the weights into bits, and every copy and every part of the model gets like one shard of it. But then if you want to save your training result, you want all of it. And so the operation you need to do is you need to gather all the parts and put them in one weight. And the fun thing is that this reverse transform static can do that. Similarly, if you train a model with QLoRa, you have the quantized weight, and then you have the LoRa pass. And at the end, you want to consolidate that in one weight matrix, one non-quantized weight matrix. And you can do that this way too. If you like have the quantization on the forward, the dequantization on the backward, you can interpret the quantized weights just as floating point weights. And the way we did this is that we do it submodule by submodule, which is awesome because we can operate on things that don't fit in memory quite as easily, because we have like very interesting hacks to do lazy loading and lazy saving with of course.
And this makes it also composable, right? Makes it composable with, if you have several transforms, this transform will run in order and then in the reverse order, so that you can actually reason one transform at a time about what happens to stick dict as you progress towards your loading the checkpoint or saving the checkpoint. And this is not a small feat. This is actually one of the things that would be a major like head scratcher. So this is how we tackle it in Thunder.
And that's why the hair is getting slower from all the head scratching. But yeah, so and then there's another trace point at the very end. We have a hook point where we have all the optimizations, and then we can do things like put everything you can in a CUDA graph in order to get rid of the host latency. And this has to be done at the very late state. And at the moment, we don't have any hook points in between. And so for the rematerialization, we would want to have one that sits right after the autograd forward and backward are computed. And so, so what happens is that if we look at and I can open it in GitHub too, what we have is that there's a function, and it's not a small one, I have to admit. It's this forward and backward from trace that takes a trace and then produces a forward and a backward trace from it. And the way it works is that it does its thing, and then it has this question, is save for backward enabled, yes or no? And if it is, it calls this transformation, which takes a forward trace and a backward trace, and gives us a forward and a backward that has been updated in order to reduce the number of saved tensors.
Yeah, I have a question for you here. We discussed that you could also, in new GPUs, right, offload to main memory. So probably, whereas this mechanism is a flag on JIT and doesn't allow you to, like, it just allows you to have it or not have it, but doesn't allow you to swap in different things. If we bring it to the transform and allow people to plug in whatever they want, you could also, it's not like super easy to code something like that, but we could allow different strategies to go in for dealing with saved stuff, right?
Right. And in particular, here you still have the question like, what things do we want to recompute and what things do we want to save? Because you had the picture with the scale, and it's a trade-off, right?
Right. Right.
Interestingly, like the trade-off is uh, uh, is a bit uh, uh, it, well, it's a bit delicate because once you start computing things twice,
Hmm.
you actually well, if you save an intermediate result and then compute the same thing twice, you save like the total memory, but you don't have an additional compute penalty, right? Um, so once you accept that you have to compute everything twice, which you might not, like you could
Hmm.
have the first half of the model
Right.
you
Exactly.
don't save the activations but recompute, and the second half you just do the usual thing, right? But
Yep.
for the bit that you have, you can actually like save a few more activations, but it doesn't give you a benefit anymore. Um, but yeah, so you have to know what to do, and this is done here via a rematerialization policy that gets all the tensors, um, and then has to decide, do we recompute or not? Um, and of course, it would be neat if we could just code this into a transform too, because then you can have like a zoo of them,
Yep.
and it's like easily composable if you want to have two passes, that one does the not so aggressive rematerialization, and then if memory gets really tight, you have a second pass or something like that. But yeah,
Exactly.
so
Yeah. Yeah.
what it has to do, if and there's a second thing, there's two ways to view this. So obviously the one thing one part of the scale is like the memory, so it's the tensors. The other part of the scale is not tensors, but it's actually computation, so it's operations. And
Yep.
so that is like a very interesting thing, because you actually have different objects that matter. And you see this here, that here we argue about, or the policy is in terms of the tensors of the proxies in our case before we materialize things. Um, but then we have to find the symbols, which are the functions, the operations, right?
Yep.
And so we do that here, and if we like recomputed a thing, and by default, and you saw this in the little MLP example, we recompute everything we can, and so then this will like add the uh, get the things we need, the new set of things we need, and then we will just repeat, copy over the operations that uh, we will just copy. Sorry, we will just copy over the operations that we need in order to recompute things, and drop the arguments that have
Yep.
been passed with the outputs. And so it's conceptually very simple. But of course, the optimization problem there is like not as simple.
Yeah, of course, because you need to do it beforehand also, right? So in the future, you could also actually either estimate your memory consumption by looking at what happens in the trace and then decide what to drop and what not to drop based on your online memory consumptions and not based on what the programmer thinks that the best is, because you might go into situations where what you save is a function also of the size of the input, of what's going on with other transforms. So it's not always easy to decide. Like with transformers, it's like customary to say, okay, let's save in between blocks, blah, blah, blah. Is it the best possible use of memory? We don't know. You cannot really know in detail. Um, so this would allow
Yeah,
us to do things a bit more, just in time. Like the size of your tensors, what other transforms are contributing to the thing. So we could either estimate it at completion time. Yeah,
yeah,
probably that's what we want to do, right?
right. And you could like try to get it down until it fits the memory, and then
Yeah.
with some algorithm, and then you do it. One thing to know is that if you have this mountain pattern in mind, what you do with the recomputation, you have a less steep ascent. And then on the descending path, you have like a sawtooth pattern. Because for these little recomputation blocks, obviously you need to save the things for the backward. And so this will all be in the backward itself. It will all be baked in, but you will have like a pattern for the memory use that goes like that.
Nice. All right.
Yeah. Should we try to get such a pattern?
Absolutely.
So yeah. So let's try this. Let's have a thing with many layers here, and I'll just do this lazily by inserting torch and then Redl, and oh no, I need to. Oh, let's do this torch and then sequential. So it's nested, nested sequential module. You never know what they're good for until you have something like this. And now we have linear, and that is just 2048, 2048.
48. Yeah.
And so this should do the trick. If I have 4 dash in range, let's say 20, right?
Nice.
And yeah, now I screwed up the parentheses here.
Yeah, you need to close the sequential. Yes, great.
Yeah, and if we look at the module, you see that it's like a pattern where you have these little blocks, and so if we have this, I hope that we can see something here in this VRAM pattern. We don't have that, right? Because we only have the maximum use, and actually I'm not on the keyboard at all.
Yeah, it looked a bit too flat, but actually now you right, you need to profile it because the allocator will just keep the memory
right
at the top of the mountain, because as we know, PyTorch has its own CUDA allocator that will not deallocate stuff, but it will basically reuse the memory blocks that have been allocated for later computations. So we only see things increasing and not decreasing unless we claim the memory explicitly.
So if we have this, we see not much.
Yeah, give it time. Oh, flat. What's going
on? What is going on?
I'm not sure.
Is it small?
It's probably too small, but 0 is suspicious. Well, no, you have 3. Yeah. Yeah, maybe you just boost it by a lot. I don't know. It looked like it could have made a difference.
Oh yeah, it
did
1 megabyte or so. Okay, so how do we get the and then I need to have a silly loss, right?
Yep.
And need to have the loss backward. And then this would ideally.
Yeah, we saw something. Yeah.
Again. But now how do I show the memory profile?
I don't know. Let me see how we can do it. The torch profiler.
So what we could do, could use our debug transform, right?
Oh, yeah, you're good. You're right. Because we can also visualize the allocations, right? With a
Yeah,
profiler, with a
with this faster.
yeah. Let me see. So
So what can we?
go to memory snapshots. Oh, basically, this is interesting. So maybe I can share
Oh,
something. Oh, go ahead.
well, if you have a version that works, I'll take that. But
Yeah, I'm gonna.
we can also, like in the post callback. So we have the no, we should have a transform here too, right? And it was oh, let's do this on the module, and
Right.
then the post callback. And the post callback should have the bound symbol and args, quarks. And strictly speaking, I always need to do this. And then we can just, and it needs to return a string, right? And return torch CUDA.
Ah, interesting. Yeah, I just sent you via Slack, but that's for later. Don't you keep typing for sure.
Right.
There's an interesting blog on the PyTorch website that shows you how to have this visualization of memory allocations quite easily with a memory profiler that is memory
Right.
history with from PyTorch. And then there's a visualization tool hosted at pytorch.org/memory_viz that you can drop your recordings, your data, and it will show you the nice
Right.
visualization.
And
But
I
the
had that.
sausage, yeah.
Right. But
But
so
the sausage here is goes through transforms. So we do the
right. And we look at
printing now.
the last traces, and with any bit of luck, last traces jm -1, with any bit of luck, we should have like there's the raw numbers here.
Yeah.
And we see it doesn't increase over the lifetime, which is because we basically opt to recompute everything. And then at the end, it drops a bit because we have a smaller activation. And then the question is, do we also get the pattern and the backward trace? And we do, and we have, now we need to figure out, yeah, here it increases a bit.
Yeah, they're minute. Yeah.
And then it's because it's like a really small example. And then it decreases.
Yeah.
Does it decrease? No, it increases more.
Oh, yeah.
Does it decrease ever again? So 2219, oh, it allocates the gradients, right? And the gradients are large enough for it to keep growing. But so the second time around, it should like not do that, right? Let's try it. And so here we have constant memory, and it still increases. So a new mystery, Luca.
Yeah, I'm seeing that.
Yeah, we need to have a better thing. And so we always need a cliffhanger, right? Next time we will have like
A
the dragon
cliffhanger.
tail on the backboard.
Yeah, but we just saw how easy it is to observe things, right? With memory, printing the memory and figuring out how can you know that this is the case otherwise, right? You would need
Right,
to dive into 20 layers of things and understand like where how things are used. And right now we have a direct number that we can observe that we obtain with 3 lines of code. It's pretty powerful. But then we need to interpret it. So this is left for the next episode, I guess.
right. And
All
if
right.
not, we'll try the debugger
The
method
PyTorch.
too. Right.
Yeah,
And
for
then we
sure.
will have all neat graphs.
Yeah,
So,
yeah.
Luca,
All right.
you still have the Friday ahead of you, but I
Yeah.
already wish you a good weekend. And
I smell cookies. I smell cookies, Thomas.
yeah, I will bake all weekend, so lots of cookies.
Awesome. Awesome. I'll spend my couple days here in San Francisco and then I'll be back on Sunday evening back in
Yeah,
Italy. So that's good. Awesome.
and
Thank you so much,
see you
Thomas.
next week. Have
Bye,
fun. Have a
everyone.
good
Bye bye.
weekend.
You too.